going to talk about translations. And as you can see in the bottom right-hand corner, a translation is a slide. It's as if we took, and notice the direction of the arrows. That's very important with these translations. It's as if we took the lighter green arrow to the bottom left of this picture and slid it to the darker green one on the top right. Okay, that's what translations are all about. They are about slides. For example, triangle ABC becomes triangle DEF. Okay, each one slid horizontally, or this particular music note also slid. So those are all examples of translations. One of the things worth noting is that you do not have to always go horizontally and or vertically. You can go kind of at an angle down or an angle up. And when you do these translations, there's a part that's horizontal and a part that is vertical. And together they make a rule to do the translation. And the way to do those rules we'll talk about with coordinate geometry tomorrow. The big thing that we want you to do as of today's lesson is we want you to be able to recognize that when this figure slides like this, you're dealing with a translation. Here's another one, pre-image, triangle ABC becomes A prime, B prime, C prime. And you can see that it is sliding. There is no spinning going on here. There is no flipping going on here, okay? It is purely a slide. Here's one here. And this is, we did a picture like this earlier. And if you put from the earlier one, it too would have been a translation. So remember, no flip, no rotation, no turn. It's just a matter of recognizing that you're moving horizontally and or vertically. For example, this pentagon. And when you move any one of the points, you have to move them all according to the same rule. So the entire figure is moved. Here's an example of how it would work in coordinate geometry, which again, we will get to in our next session. You can see that R goes down 3 to the right 4. And that makes R prime. Look at P. It goes down 3 to the right 4. That makes P prime. Look at Q. It goes down 3 to the right 4. It makes Q prime. So when we do coordinate geometry in our next lesson, then you will see that following that rule where you go over and up and down and so on and so forth, that's how we do our translations. For now, it's enough that you recognize that it's not spinning, it's not flipping, and what it's doing is it's sliding from one place to the other. So here's a summary of what we've done so far and what we're about to do. We've talked about rotations, where rotations are turns, okay? We've talked about a flip, that's a reflection. We've talked about a translation, which is a slide. The next thing that we're going to talk about is a dilation. Now, dilations shrink or grow. That's the big thing about a dilation, okay? So the pre-image of this penguin type figure shrinks down to the image. That's a reduction. Or an enlargement is when you take like a map of the United States and enlarge it pre-image to image. This is the kind of thing that we do when we are doing drag and drop with our images and putting them into our PowerPoint presentations, or with photographs that we are getting pictures made of, right? Like, you know, you talk about megapixels in a camera, and it might be like one of my cameras shoots like 60 or 65 megapixels. And in turn, if I want it to fit in a smaller picture, then they have to reduce it. And sometimes I get a picture and then I have to enlarge it to fit in a particular area. So with photography, these dilations are something that you use constantly all the time. So a dilation is enlarged or reduced. If you're going from left to right, the square is enlarged. If you had started on the right and you went to the left, the square would be reduced. All right, so the center of a dilation, I wouldn't worry too much about that. The big thing is if you look at the original triangle, which has sides of 4, 6, and 8, And the finished triangle, which is 8, 12, and 16, the finished triangle works out to be twice as big. And that is a picture of a dilation. Every figure we've done, every type of transformation we've done so far, translation, rotation, reflection, point reflection, all of those are what we would call isometries because they keep the size the same. This is not, dilations are not an isometry. It's the only one that's not an isometry. It makes things bigger or smaller, like this. Now, the pre-image, be careful in this one. We have a tendency to think that the answer is always the bigger one, but that's not the truth. If the factor is between 0 and 1, you actually reduce. So if the pre-image is the blue one and we use the factor, let's say 1/2, then everything would be half as long and it would turn into the greenish yellow one, okay? So if the factor is between 0 and 1, then you actually end up reducing the size of the shape. So here's a good example. If the scale factor is 2, the pre-image on the left is triangle A and it's triangle A prime on the right, and the scale factor is 2, so everything in the image will be twice the size of the pre-image. But if the scale factor is 1/2, well, look, it starts with A and it becomes A prime. If the scale factor is 1/2, everything is half as long. So when the scale factor is between 0 and 1, then the image is going to be smaller. I don't know why they reversed pre-image and image here. That's crazy. You can see the arrow is pointing in this direction. They have it backwards. You're starting with the A. The scale factor of 1/2 shrinks it to A prime. And on the other one, the scale factor is bigger than 1, so it makes the shape bigger. So if it's less than 1, no, and we don't want to get into negative. So if it's less than 1, the image is less size. And if it's greater than 1, the image is greater sized. Here's another one, pre-image and image. We start with a square. The factor has to be greater than 1 to create a bigger image. Or here's another one with a reduction where we get the pre-image shrinking down to the image, and that factor has to be less than 1. And here is a little hint as to what we are going to do with coordinate geometry, okay? We always start with the A, B, C, D and go to the A prime, B prime, C prime, D prime. So what you'll notice here is in each case, I'm multiplying by 1/2 or dividing by 2 if you want to look at it that way. And since the factor was 1/2, everything is being reduced, okay? All right. So here's a summary of what we've done so far. A translation is a slide. A reflection is a flip. A rotation spins the figure. Now we did 180-degree rotations, but there were 90-degree, there are 270, there's 120. So there's lots and lots and lots of different rotations that you can do. And then there is a dilation where they shrink or expand. The first 3 types, translation, reflection, rotation, are all what we call isometries. Isometry keeps the same size. Iso comes from the Greek, the prefix. Iso means same, metry means measure, like metric system. So iso, same, metry, measure. So same measure. So they have the same size when you are done with your transformation, if it's a translation, a reflection, or a rotation. So they're all called isometries. A dilation is not an isometry. Okay. Also, let's try to sound a little bit intelligent here. Okay. It's not a dilation. We're not like, dialing the phone here. Okay. It's a dilation. Look at the letters of the word, D-I-L-A, dilate, dilation. Okay. Not dilation. All right. So we got one little piece left for today's lesson, and that little piece involves just being able to recognize a tessellation. You don't have to be able to draw one of these. Lord knows, if I tried to draw one of these, it'd be pretty bad. It's used in art a lot. A very famous mathematical artist by the name of Escher. He did lots of patterns with tessellations. But this is what a tessellation is. Okay, tessellations have no overlaps or spaces, and they have repetitive shapes, often called tiles. So tessellations are patterns like this where everything fits together perfectly. There could be no overlaps and no spaces in between. And there's a repetition of shapes. They appear over and over and over again. It doesn't all have to be the same shape. In this case, it's a combination of triangles and squares. Here you have kind of forward arrows and backward arrows. Notice they fit perfectly. There's no overlaps and no spaces. And it's a repetition of these figures, often called tiles. And here are two more. I actually think the one on the right is an Escher design. I'm not positive about that, but I think it is. Okay. All right. So this ends our lesson number 15. Of course, there'll be a corresponding assignment to go with it. But that introduces transformation geometry to you so that you should be able to recognize reflections, rotations, translations, dilations. And you should also be able to understand that the first three are isometries. The last one is not an isometry. And you should be able to recognize a tessellation when you see one. The next lesson we do, we'll take these ideas and put them into coordinate geometry. So the next lesson will be a little bit longer.